Right out of the gate, Kimi K3 is putting up results that rival the most powerful proprietary systems on the planet. I'm talking about executing highly complex, multi-step professional workflows. Think deep legal analysis, investment banking tasks, and heavy STEM reasoning. So how exactly did they pull this off? Let's get into it. The open intelligence frontier, unlocking new agentic capabilities at scale. To understand why Kimi K3 is such a big deal right now, you just have to look at the current landscape. Across benchmarks spanning long-horizon coding, general reasoning, and complex knowledge tasks, this model establishes a brand new open frontier. It's consistently outperforming almost everything out there, closely trailing only the absolute top-tier proprietary models, specifically Claude Fable 5 and GPT 5.6 Sol. That is some serious company to be keeping. But, benchmark numbers only tell half the story, right? What really matters is how this translates to real-world impact through agentic case studies. We are talking about a model autonomously handling complex, multi-step information searching. It's successfully tackling professional deliverables for investment banking, heavy data analysis, and intricate legal workflows. It even excels at verifiable visual reasoning. It can write and execute Python code in an isolated sandbox, with verifying the loop execution just to parse charts and solve visual STEM puzzles over hundreds of interaction steps. It's incredibly robust. Section 2. Architecting the neural core, building a 2.8 trillion parameter brain. So how do you even begin to structure a brain this huge? The secret sauce here is a unique hybrid attention mechanism. In every block, it blends 3 Kimi delta attention, or KDA layers, with 1 gated multi-head latent attention layer. The KDA layers use a highly efficient chunk-wise parallel form and an input-dependent full-rank gate. This handles the heavy lifting of computationally efficient sequence mixing. Then that single gated MLA layer acts as a sort of periodic checkpoint, retaining unrestricted global token-to-token interaction. It is just the perfect balance of raw efficiency and deep comprehension. Furthermore, Kimi K3 implements something called attention residuals. Think of this like being able to instantly flip back to any chapter in a textbook you've ever read, rather than just relying on your fuzzy memory of the very last page. It allows each layer to selectively attend to representations from earlier layers. And to make this memory efficient, they use block attention residuals, grouping layers together so the network accesses historical context without completely bottlenecking the system's memory. Now, to scale its width efficiently, Kimi K3 relies on stable latent MOE. This setup acts like a massive firm with 896 highly specialized consultants, but it smartly only brings 16 of them into the room for any specific token. Of course, extreme sparsity like that can cause optimization nightmares, so the team introduced normalized latent MOE and a novel activation function called Sci2GLU, that's sigmoid tanh unit GLU, to suppress exploding internal activations and control large value growth. And to ensure all these experts are actually being utilized evenly, they implemented quantile balancing, using a brilliant histogram estimation technique to route tokens perfectly across the global batch. Let's shift gears to visuals. Traditional vision models are usually just bolted on post hoc using pre-trained models like SIGLIP, which the team found leads to highly unstable training and crazy gradient spikes. Kimi K3 does not do that. Instead, they built their native vision encoder, MoonEP v2, completely from scratch. By using a next token prediction objective right from day one, the model processes text, images, and videos natively through a single shared backbone. The result is vastly superior training stability. And to optimize all these massive parameters, the team upgraded to the per-head muon optimizer. Rather than trying to update the massive attention projection matrices all at once, it partitions them and orthogonalizes each head separately. This ensures perfectly balanced learning dynamics across the individual attention heads, squeezing out absolutely every ounce of performance. Section 3. Pre-training 1 million tokens, scaling data and context. Just look at the leap from Kimi K2 to K3 here. It's absolutely staggering. We're going from 32 billion activated parameters to over 104 billion. By combining their architectural updates with highly curated pre-training data, specifically heavy on math, code, and native vision, and retuning their scaling laws to favor cosine decay, Kimi K3 achieved a massive 2.5 times improvement in overall scaling efficiency. And check out that context length, expanding to a mind-bending 1 million tokens. Now, because the model's KDA architecture uses NOPE, no positional encoding, it naturally extrapolates to longer sequences. They capitalized on this by feeding the model specially curated long context data and progressively extending the window. They went from 8K to 64K to 256K, all the way up to 1 million tokens during the final cooldown phase. Section 4. Post-training agentic reasoning, reinforcement learning at scale. Okay, so the post-training pipeline starts off with supervised fine-tuning, or SFT, just to lay the baseline groundwork. Then it scales up reinforcement learning across 3 core domains: general tasks, agentic behaviors, and coding. Crucially, they apply reasoning effort RL, which trains the model at low, high, and max token budgets specifically to control overthinking. You don't want the model wasting compute when it doesn't need to. Finally, they use multi-teacher on-policy distillation, MOPD, to seamlessly unify all these domain-specific expert policies back into one single, highly capable model. But evaluating these complex agentic behaviors requires a really smart judge. To accurately evaluate non-verifiable tasks, the agentic generative reward model forces the AI judge to follow a strict 4-step protocol. It has to read the outcome, explicitly generate an evaluation rubric, score candidates against that specific rubric, and record the results. This highly structured approach, paired with a strict verbosity control threshold, brilliantly prevents the model from reward hacking simply by generating longer, wordier answers. Now, to ensure Kimi K3 had a diverse and challenging diet of training tasks, the team didn't just sit down and write them by hand. That doesn't scale. Instead, agents autonomously built a self-evolving knowledge graph. They recursively expand this graph via web search, retrieving materials targeting highly specific concept granularities. They then synthesize these retrieved real-world materials into specialized, highly complex agentic environments. This knowledge graph-guided RL task synthesis continually pushes the model to its limits. They also integrated deployment awareness directly into the training pipeline. They used MXFP for quantization-aware training right in the RL stage, which means the model learns to compensate for lower precision deployment formats from the very beginning. They even fine-tuned the pre-trained multi-token prediction layer into an Eagle 3-style draft model, which massively optimizes inference efficiency for those long-horizon tasks. Section 5. Engineering multi-trillion scale. The system's infrastructure. And this brings us to the ultimate systems engineering question. How on earth do you combine 3 major system challenges rarely encountered in a single model? Think about it. You have hybrid KDA attention, a 3 trillion class sparse multimodal training setup, and million-token agentic workloads. Scaling any one of these is hard enough, but doing all 3 simultaneously without completely breaking the system, that is a staggering feat of engineering. The answer to that question lies in some brilliant hardware and software co-design. First, they developed MoonEP, a framework for perfectly balanced expert parallel training utilizing zero-copy communication. To handle those extreme sequence lengths, they invented KDA context parallelism, achieving linear compute scaling via fixed-size all-gathers. They also built custom fused kernels called Flash KDA to completely eliminate idle time during state propagation. And for those massive agentic tasks, they built resumable micro-VN sandboxes that allow million-token trajectories to be paused and resumed across training iterations without losing a single drop of progress. On top of that, they had to manage the extreme prefix block churn caused by these million-token multi-step rollouts during training and speculative decoding. To solve this, they implemented advanced state-aware caching. By moving the KV cache pool externally, they prevented preemption and kept the system churning through massive amounts of data efficiently. And honestly, the best part? All of this incredible work isn't locked behind some corporate API. By releasing the full Kimi K3 model weights, this research establishes a vital, open-weight counterpart to the most advanced proprietary systems available today. It is a massive gift to the global AI research community, allowing absolutely anyone to build upon these innovations.